Yeah, so in this next video, I'm going to do exercise 10F question number 2, which looks like this. So two particles P and Q have masses masses km and 3m respectively, where k is less than 3. So the particles are connected by light and extensible string which passes over a smooth light fixed pulley. The system is held at rest with the string taut and the hanging parts of the string vertical with P and Q at the same height above a horizontal plane, as shown in the diagram. So they've given us a diagram this time. The system is released from rest. After release, Q descends with an acceleration of 1/3 g. So I'm just going to redraw that diagram. And so you've got P here and Q here, and we know that K is less than 3m. We've been told K is less than 3m. So I'm just going to draw this like that. So K is the weight of P and 3mg for the weight of Q. And because K is less than 3m, we know that this is going to accelerate this way. Having said that, they did tell us that Q descends. So this one's going to accelerate this way, and P is going to go upwards. Maybe I'll just write in the 1/3 g there. So let's just put the 1/3 g there. Right. Then we also need our tension. As I said in my previous videos, that tension is a pulling force. So it goes away from the particle, and because it's one piece of string, the same piece of string, the two tensions are going to be the same. So you've got this diagram here. Right. And then it says calculate the tension in the string as Q descends. So maybe we'll just have a look at particle Q. So particle Q has a tension going upwards, 3mg going down, and an acceleration of 1/3 g. I've drawn it out. You might not choose to, and most times we don't need to redraw it, but I've redrawn it just for the sake of this example here. And so let's look at the resultant force. Because it's moving, accelerating downwards, I'm going to take downwards as positive. And you've got a weight going downwards, so 3mg going down. You've got tension pulling it back up, so we're going to subtract the tension because it's going in the opposite direction. And this is equal to the mass of the object, which was 3m, times the acceleration, which was 1/3 g. And if you rearrange this, I'm just going to simplify the right hand side first, and the 3's are going to cancel, so leaving me with mg. And if we rearrange this now, we should get T is equal to 2mg, which is great. Then it says part B then goes on to say show that K is equal to 1.5. So for this, maybe we should look at the second particle, which is P. I'll just redraw it quickly, it doesn't take long. So got tension going up, kmg going down, and it's accelerating upwards. This particle is accelerating at 1/3 g meters per second squared upwards. So this time I'll do the resultant going up, and you've got the tension going upwards and the kmg, the weight, pulling it down. So we're going to subtract the kmg, and that's equal to mass, which is km, times by acceleration, which was 1/3 g. And because we took upwards as positive and the acceleration is upwards, this is going to be acceleration is positive as well. Right, we can put in our 2mg for T. So 2mg minus kmg is equal to 1/3 kmg. Everything's got an m and a g in it, so we can cancel the mg's out. So 2 minus k equals 1/3 k. And so 2 is equal to, if I move the k over to the right hand side, I'm going to get 4/3 k, and so this implies that k is equal to 6/4 which is 3 over 2, which is 1.5, as we needed. So that's part B. Then it says, state how you use the information that the pulley is smooth. Well, the fact that the pulley is smooth means that there's no friction, and so the acceleration for both the particles is going to be the same. Okay, because they're connected by one piece of string. So the fact that the pulley is smooth means there's no friction, and then the acceleration for both the particles is going to be the same. Now let's have a look at part D. After descending for 1.8 seconds, as soon as you see some time given, I'm thinking that this might be a suvat kind of thing. So after descending for 1.8 seconds, particle Q reaches the plane. It is immediately brought to rest by the impact with the plane. Now Q is brought to rest. You start thinking about what happens to P. So the initial distance between P and the pulley is such that in the subsequent motion, P does not reach the pulley. Show that the greatest height in meters reached by P above the plane is 1.26 G. 7-mark question, so there's going to be quite a bit of work to do. Now, if you followed through on Nazia's PowerPoints that she sent, you would have seen that when one particle hits the ground suddenly, what happens with the second particle? What happens with this particle here? Well, what will happen, I'm going to try and draw it for you here, is because suddenly this one has just hit the ground, what's going to happen to this piece of string is that it's going to become slack, because P has a little bit of momentum. It's just going to carry on going a little bit further up. And so when Q hit the ground, P was here. P was at this height. But now what's happened is that P has jumped, it's carried on going a little bit, and then it's suddenly stopped over there, and then it will reset back into where it used to be, roughly around there, and with Q on the floor. And then it will come back to this position here. But the question's asking, what is the height at this point when P is at its maximum, highest point? Okay, so this is what we call a multi-phase problem. There's two different scenarios. In the first scenario, P and Q are moving together, and so as P ascends, Q is descending. And in the second phase, so this is first phase over here, in this situation here. And then in the second phase, P is moving by itself. Q's already hit the floor. It can't do anything else now. It's been brought to rest. And P does a little jerk. It does a little jump in the air, because it just carries on going for that little bit, that split second longer. Okay, so we have to look at this as a multi-phase problem. And so in phase 1, let's think about what we know. In phase 1, we were told that after 1.8 seconds, after Q descends for 1.8 seconds, in the acceleration we were told this as well. This was 1/3 G. I'm going to leave it as 1/3 G because the answer is also in terms of G. We don't know V. We know it started from rest. So we have 3 bits of information, which means that we can work out anything that we want. Now we're interested in the distance moved. So let's work out S. So if we have U, A, and T, and use our favorite equation, S equals UT plus half AT squared. This one's pretty much used every single time. So S equals UT plus half AT squared. If we put all our information in there, U is 0, so the first term disappears. So it's going to be plus a half 1/3 G T squared. Now I'm going to change T into a fraction, just because this is a little bit easier to deal with. You're going to get that. And if you put that into the calculator, leave G, so just type in a half times a third times 9/5 squared. and that's going to give you 27 over 50 G. So that's our S calculated. So we know that from its original position, so if we do original position, this is Q, this is P. We know that Q had to move 27 over 50 G down, which also means that P has now moved up 27 by 50 G upwards. Right, so overall it is now in this position, it's going to be 2 times 27 by 50 G above the ground. So this is going to be 2 times 27 over 50 G. So let me just zoom in there. So it's 2 times 27 over 50 G above the ground. Let me just write that again. So this distance here is 2 times 27 over 50 G. Okay. Right, so that's that. Now what happens in the next phase? Well, in the next phase, essentially, because the string is now taut and P is moving by itself, we're gonna have Suvat again. We're gonna have a change of acceleration. Q is no longer pulling P up. So what P is doing while it's moving by itself, it's slowing down. Well, why is it slowing down? It's slowing down because of gravity. And so it'll be decelerating and due to gravity, and so A is going to be minus G in this second phase. We also wanted to consider the particle at its highest point. So at its highest point, its final velocity will be 0. It would have stopped moving. It'll be on its point, on its way down again. So it'll have stopped momentarily, and then it will come back down. So because it stopped, its final velocity is going to be 0. But we don't know either S, U, or T at this stage. And in these multi-phase questions, the whole point is that because they're sequential, when the first phase finishes, as soon as the first phase finishes, the second phase begins. And because it's like that, that means that the final velocity we have over here, it's not 0, it's just whatever the final velocity there is going to be our initial velocity over here. So the final velocity at the end of phase 1 is going to be our initial velocity at the start of phase 2. So let's work out our final velocity. So I'm still dealing in phase 1. We can use V is equal to U plus AT. U was 0, A was 1/3 G, and T was 9/5. So we can get V as equal to, I make that 3/5 G. So as I said, that becomes our initial velocity in phase 2. Now we're armed with everything we need. We've got 3 bits of information. We can work out S in our second phase. So we're not going to use S equals UT because we don't have T. So this time we're going to use V squared equals U squared plus 2AS. So U squared and if you rearrange that to work out S, you should get S as 9/50 G. So let's remember that it's going to move 9/50 G in this last little bit where it does its jerk while it's moving without the aid of Q. And so the maximum height is going to be 9/50 G plus 2 times 27/50 G. And that's going to give us a total of 1.26 G. Right, just a minute. Okay.